Good evening to everybody. I'm going to start with a quick recap of just NMR spectral interpretation, and then we're going to go into specifically how to calculate the chemical shifts and coupling constants for the alkenes so that you can do your stereochemical determination for the product. And then we'll talk about report, what needs to be in the report, and that should finish it. If you have questions, of course, you can ask those. And I'll also look at the spectra that you have and the spectra that I put up on as you learn. So let's go ahead and get started with this. For NMR spectroscopy, there are three things that we typically look at when we're doing an interpretation. We look at chemical shift, which gives us some information about the type of hydrogen, the integration, which tells us the relative number of hydrogens, and then spin-spin splitting, which tells us some information about what is bonded to what, so we can start putting the molecule or the pieces together. So this is an NMR spectrum. We've got a series of peaks here. We have a correlation table on this screen. This is the sort of thing that you should memorize so that you know the different chemical shifts and you can do an interpretation. You can find some that are more nuanced, but really there's a lot of overlap in trying to distinguish, say, a methyl from a methylene from a methine is really difficult to do through chemical shift. And we have integration to tell us if it's a CH2 or a CH3 or a CH1. There is one row here that's kind of useless, and that's the OH row. You'll notice the range 1.5 to 5 ppm. That's too broad to be useful. If you want to determine if you have OH, you wouldn't use NMR. You'd use something like IR. You get that nice big broad band around 3,300 wave numbers in an infrared spectrum, and that will tell you that you've got an OH or not. And then for NMR, if you did have it, you would simply try to identify which peak. But for NMR, OH and other exchangeable hydrogens like NH tend to be fairly broad. And so we just have general regions, though, that, especially for this class, one that you'll see fairly often is the alkoxy or alkyl halide. This is the range 3 to 4.5 ppm, or aromatic is something we see a lot, typically around 6.5 to 8. So we can apply that to this spectrum. We have these peaks out here around 7 ppm. Again, if we went back to that correlation table, 7 ppm would be this aromatic range, and so these are most likely aromatic hydrogens. We have our next peak around 3.7. Again, that's in that alkoxy range. We would look on the spectrum and we would see, or in that correlation table, and we would see this is OCH. That oxygen could be a halogen. There's a reason why in a little bit we'll know it definitely isn't, but halogens, electronegative atoms, bromine, chlorine, oxygen, nitrogen, all put peaks in about this region. Next area over is the CH next to a double bond, not on the double bond. So this could be a CH that's next to an alkene, or it could be part of an aromatic ring. Not a prettiest ring, but that's benzylic, would also show up in this region, as would a CH that's next to a carbonyl. So, something like acetone would have a peak in about this range. But this is CH next to a double bond. And then the last peak is around that 1 to 2 range. This is the range where we have just typical alkyl CH, the methyls, methylenes, methynes. So we know the various types of hydrogen. The next thing we would look at then is integration. Integrations, of course, have to be whole numbers. You can't have half a hydrogen, although we do have here this one labeled as about 2.5 hydrogen. So we know this is not normalized, and we would need to adjust that. The common way of doing that is to simply divide all of the numbers by the smallest, Or if you know, for example, this one is supposed to be a CH3, you could simply multiply 2.5 by the correct factor to make it 3, and then multiply all of them by that same value. And then we get numbers that are roughly whole numbers. They won't always be exact, but they should be fairly close. And then we know, for example, that we have those integrations that are now corrected, and the computer will do that for you. If you tell it, this is a CH3 or this is a CH1, you can have it do all of that math for you. But it's often not done, or it's assumed. The Brooker software, the top spin, will assume that the first peak you integrate is 1, which isn't always accurate, and you may need to go back and adjust it. But the number should be close to whole numbers. And when we do that, we can see that we have a CH3. So that group that we identified earlier is methox or alkoxy, the OCH3, or OCH initially. Now we know OCH3. And we know this can't be one of the halogens. It can't be chlorine or bromine, or this would be a molecule onto itself. There's no bonds left that are for anything else. If we look at that peak around 1.2, we see an integration of 6. Of course, you can't have a CH6, so the likely explanation is this is 2 methyl groups. That gives us a total integration of 6. It is possible we could have 3 methylenes. 3 CH2 groups would also give us an integration of 6, although that's going to be far less common since we have 1 peak here. We would have to have CH2s that are all equivalent. It is possible, but not very likely. The more likely explanation is CH3s, 2 of them. And then also those 2 peaks out around 7, integrations of 2. You can't have a CH2 as part of an aromatic ring because we do have the alternating double and single bonds. All of the carbons have basically 3 bonds to other carbons. And so there can only be 1 hydrogen. So we know that must be 2 CH2s, same with the other one. And so we know some of the pieces. We know this is an aromatic ring up here. And we know that ring has 2 or 4 hydrogens on it total, which means it's disubstituted. It has 2 other things bonded to that. So moving on, we would look at splitting or coupling. The adjacent hydrogens will split the peaks, and you've seen this then in lecture. If you have 1 neighbor, you would have it split into a doublet. 2 neighbors splits it into a triplet. 3 neighbors into a quartet, 5 into a sextet. So really the number of peaks is going to be 1 greater than the number of neighboring hydrogens. Actually a couple things to keep in mind with this. First, notice that for these multiplets, the spacing between the peaks is equal. For this quartet, for example, the distance between that outer peak and the inner peak is the same as between the 2 inner peaks, which is the same as between the other ones. So all of these distances are equal. If they aren't equal, then you don't have a quartet. You probably have overlapping peaks, or you have something else. The other thing is that we do have these very specific patterns. A doublet, the 2 peaks are going to be a 1-to-1 pattern. The 2 peaks are of equal intensity. A triplet, we have a 1-to-1 pattern where that center peak is twice the size of the other 2. If you have something like this, where you, like this, 3 peaks of roughly equal intensity, that's not a triplet because it's not a 1-to-1 pattern. In fact, it looks more like there is a singlet next to a doublet. All right, so let's apply that to the spectrum we were just looking at. We would look at this peak here. Again, it was integrated to 3. It is a single peak. So this would be a singlet telling us there are no neighbors, which is not surprising since we already knew from the integration and the shift that we probably have an OCH3, which means since the oxygen is going to have something else bonded to it, we're not going to have any splitting to that one. Moving over to the peak around 1.2, we're going to blow that up so you can see it better. So this is a doublet. Doublet means there is one neighbor, meaning those two CH3s are each bonded to a CH. And so that tells us we likely have an isopropyl group. And so that one hydrogen is splitting the two methyls. And then the peak around 2.7 ppm, blow that up and we can see that we have one central peak, two on the sides, two more, and then two really small ones. So we do have a pair of smaller peaks out here. So it's a total of 7 peaks. This is a septet. The septet tells us that we have 6 neighboring hydrogens. And that would then be those two CH3s. And so we have this, and the splitting comes from those adjacent peaks. And so we always look at our spectrum, we look at the splitting, tells us septet, 6 neighbors. Likely way we get 6 neighbors is 2 CH3s. Again, it could be other things. It could be 3 methylenes, but given that we don't have methylenes, we only have methyls, we can be certain that's 2 methyl groups there. But anyway, those shows the splitting there. So moving to the aromatic region, we have these 2 peaks. When we expand them, we can see there are 4 each of those sets. But 4 peaks, these are not quartets because it is not that 1-3-3-1 pattern, and it's also not evenly spaced. So this is something else. For those of you that have covered it in lecture, this would be what we call a doublet of doublets. It happens when you have one hydrogen splitting it into 2 and you get a doublet, and then you have a second hydrogen splitting it again, but with a different coupling constant. And so you end up with something like this. And so you have the 4 peaks then. And the spacing can be any number of different orientations or varieties. That's a doublet of doublet. If you don't know that, you can also just call this a multiplet. Typically, if we look at a peak and we don't know what the splitting is, it's not obvious. We refer to it as being a multiplet. And I'm fine with it being called that. But again, this is also actually a doublet of doublets. If you don't recognize that, that's not a problem. Right? And that tells us then that we also have the para-disubstituted aromatic ring. We have 2 signals in the aromatic region. Because of symmetry down this axis, we know that these hydrogens are going to be equivalent to one another. And these 2 hydrogens are going to be equivalent to each other. And so we get 2 sets of peaks, and they each integrate to 2. If we consider the other possible orientations that we would get with an aromatic ring, another possible one would be to have the 2 groups, whatever they are, in a ortho or a 1-2 pattern. But if we do this, then we no longer have that symmetry. And so now all 4 hydrogens are going to be unique. This one is next to the Y and a hydrogen. This one is next to X and a hydrogen. And so they are not equivalent to each other. So we should probably just use different colors with that just to show it. So these are inequivalent. They would have unique labels. Likewise, when we look at this one, because it is a cross in a 1-4 relationship to Y and a 1-3 to X, it's different than the others, but it's also different to this one that I'm going to mark in purple, because the purple one is a cross from X. It's 1-4 to X as opposed to 1-3. So all 4 would be separate. We would have 4 separate peaks that all integrate to 1 hydrogen. And you could do the same thing for the 1-3 or the meta orientation. And we'd see again, you would have 4 or expect to have 4 peaks. And so this is the para-disubstituted. And then we can then put those pieces together, the para-disubstituted. There are 2 substituents. One of those substituents is, of course, going to be this methoxy group bonded to one end, and the isopropyl group bonded to the other. so that we have this compound. So with NMR, we can often get a specific compound, identify something very particular, makes it very powerful, more so than most of our other spectral techniques, although having those three things that we have to look at, it can be a little more complicated to interpret. For today, specifically for this experiment, you also have to look at the stereochemistry of the alkene. This could be a cis or a trans alkene, and you can't determine that from chemical shifts since they all show up in about the same region. Not by looking at the gross chemical shift like we have in a correlation table, but you can calculate specific shifts for the compound you're expecting to have or that you've identified from the NMR and ask, okay, if it's trans, where do I expect the hydrogens to show up? If it's cis, where do I expect them to show up? And you can also use coupling constant. For chemical shift, we have this equation, 5.25, plus the effects of the geminal, the cis, and the trans substituents. So if we look at the simplest alkene, which would just be ethylene, so we've got 4 hydrogens, we have symmetry across here, the top and the bottom are the same, we have symmetry here, left and right are the same, all 4 hydrogens are equivalent, and the chemical shift for those hydrogens is 5.25 ppm, which explains where this term comes from. Then, if we substitute one of those hydrogens out, say we delete this hydrogen and put a methyl group here, that will change the chemical shifts of the other 3 groups. And how much it changes it is going to vary depending on the orientation to the methyl. So the hydrogen that is on the same carbon, so this hydrogen is said to be geminal. So whatever's on the same carbon, it's called a geminal relationship. And the methyl group has the general effect of increasing the chemical shift of a geminal group of around 0.44 ppm. The hydrogen that is cis, so the one on the opposite carbon, so we're talking about this one out here, a hydrogen that is cis to a methyl group tends to see the chemical shift reduced by about 0.26 ppm. And then the trans one, so this one out here, we would tend to also see a decrease, but of around 0.29 ppm. And so all of those have an effect, and we can add up the effects if we have more than one substituent on that. And we have this table here. You do not need to memorize this table. You will almost certainly have to do these calculations on the final exam as well as on this report, but you will be given the table. You do not need to memorize this. I don't have it memorized, and I would certainly never expect anyone to do so. But you can see those values that I pointed out. An alkyl group, so this table applies to all alkyl. It treats ethyl the same as methyl, same as propyl or isopropyl. And so these values are going to be approximate. The geminal increases the chemical shift by about 0.44. The cis decreases about a quarter, and the trans about 0.29 or about 0.3. But again, these are approximate since we're using one value for all of the alkyl substituents. But it gives us a ballpark number then for the chemical shifts. And we'll look at an example. Oh, before we do that, let me point out one thing with these 3 groups. Notice all of these are carbonyls. This first one is for aldehydes and ketones. The second one, if you expand that, COOR is this. This is esters. And then this one is for carboxylic acids. You do have different values for those. And it's important to recognize that when you're doing your calculations that you're using the right one, because these values can be quite different. These are fairly similar, but the acid's very different, but then trans is very different. So make sure you're using the correct one when you're doing your calculations. So we've got an example here. This is an alkene. We've got a methyl group and an aromatic ring on it. So if we're doing our calculations, we would again have our 5.25 plus the geminal plus cis plus trans. And so we would go down into the table to look at those values. So again, we've looked at the ones for the alkyl and seen where those are. We would also do the aromatic then and look at the relative position. So for hydrogen B, which is the one that we are looking at, we have 5.25. The geminal group is the methyl. So we'd go into the geminal column, go down to methyl or alkyl. We add 0.44. For the cis position, we have the aromatic ring. So we would go to cis, come down to aromatic, 0.37. So we would add 0.37. Trans is a hydrogen, so there's been no change, so we get 0. And again, you could go to the table and see that trans is going to be 0 because, of course, that was the reference compound. And we add those up, and we would get that we would expect the chemical shift for hydrogen B for this trans compound to be around 6.06. This slide shows the same calculation for the cis isomer as well. So here we have the methyl and the aromatic are cis to one another. And so we would have the same calculation, geminal 0.44. Now it's a cis hydrogen, so 0. And the group that's trans is the ring, and that reduces the shift by about 1/10 of a ppm. And so then we would expect from the calculation to have a peak around 5.59 ppm. The actual chemical shifts are there. 0.06 is what we calculated. The actual one for this compound is 609. So very good agreement for that one. This one, the agreement is not that good. 559 and 5.78, almost 2/10 of a difference in chemical shift. So the numbers aren't perfect, but they usually put us in the right ballpark. This is 3 more examples. This one, the calculated chemical shift would be 6.55. The calculation is shown. And I will highlight when you're doing this, a common mistake I see in class is people will get this number wrong because they use the value in the table for the CO, for the aldehyde and ketone. And so they get that number wrong. This is an ester. And so you do need to use the one for the COOR. Okay. The next one is also shown 775. Again, the calculations are shown. And again, we do have an ester for this as well. And then for the last one, we have calculations for both HA and HB. So we could have done both hydrogens in compound 2 as well. And they do have different values because, of course, for HA, the geminal group is phenyl. For HB, the geminal group is bromine, and so we have different effects for those. And again, we have the calculated values, 655 versus 68. Again, not very good agreement. Occasionally, we do have the numbers off a little bit. 775 versus 769, good agreement. And then 7 versus 707, and 666 versus 673, fairly good agreement. What you'll find is while the values don't put you precisely on, they get you close enough that you can distinguish between cis and trans. And we'll look at an example where we are doing just that. So here we have a spectrum. This is for cinnamic acid. The structure is shown above. It's also phenyl propenoic acid. and we have the two isomers, cis and trans. Question is this spectrum for the cis isomer or the trans isomer? And we would do exactly the same calculations we've done. We would calculate HA and HB, the chemical shifts for the cis isomer, and we do the same thing for the trans. When we do that, we get these numbers, and I'll show the calculations below so you can see those. And then we simply look at what did we calculate? 734. So we'd come out to about 734 would be right around here. This would be for the cis. I'm going to put CT for cis, that for the trans. Or actually, let me correct that. Cis A. Cis B would be 615. So right around here, this would be the cis isomer hydrogen B. For the trans, we have calculated values about 795. So we would expect the trans hydrogen A to be out here, trans hydrogen B around 662. So the trans hydrogen B would be right there. And so we can see then that the two peaks, those two doublets for the alkene hydrogens, agree very well with the cis calculations and not for the trans. So we can be certain that this spectrum is for the cis cinnamic acid. And so this is what you're going to be doing for your compound as well. You're going to calculate the chemical shift for the two hydrogens for the cis isomer, do it again for trans isomer, and then compare it to your spectrum and see which ones match best. We'll also look at coupling constant as sort of a confirmatory method. Coupling constant is the distance between two peaks in a single multiplet. So when we're looking at our splitting, we have this doublet. We're looking at the distance between two peaks within the same doublet. If we had a triplet, it's the same thing, but we're looking at distance between two adjacent peaks. We could look at those two or these two. Since the spacing is going to be equal, that would be the coupling constant. Now, coupling constants are in hertz. The splitting, the difference between the spacing between those two peaks in ppm is not constant. It's going to vary with the field strength of your magnet. So if you have a stronger magnet on one spectrometer than on another, you're going to have different spacing. But that spacing will not change when we look at this distance in hertz. And so you do have to convert those to hertz. But we do see in this table a difference here for the cis. It's 8 to 13 hertz. Trans couplings are in the range of about 14 to 18, and they really don't overlap, so you can use this as a method for distinguishing cis and trans. The calculation is given down below for HA or HB. The field strength for the magnet is going to vary for our instrument, and you should write this down. We have a 400 megahertz instrument, so it's going to be 400 hertz per ppm. And so your magnetic field is going to be 400 hertz per ppm for the spectra that we acquire in our lab. If it's acquired on a different spectrometer, someone will have to tell you what the field strength of the magnet is. Okay, so we've got another example. This is again cinnamic acid. We have our two peaks. You can see they're in a different place than the earlier one. So this is almost certainly the trans isomer. But we'll go through the calculations. Again, you're looking at the distance between these two. And so we would want to put that distance in. So we simply subtract those two numbers. This was acquired on a 300 megahertz magnet. So calculations are given here. So for the hydrogen A, 7.82 minus 7.77. So again, we're taking the difference between these two, multiply by 300, and we get 15 hertz. Do the same thing for the other peak, take the difference between those two peaks, multiply by 300, and we again get 15 hertz. And these two numbers need to be the same. If they're not the same, then you probably have two peaks that are not coupled to each other. You don't have the two vinylic peaks. You've chosen the wrong ones. Although I'll put one caveat in there, you will have possible rounding errors, so those last numbers could differ by a small amount. For 300 megahertz spectrometer, they can differ by like 0.3 or 3 in that last place, assuming you're using significant figures. 400 megahertz, it'll differ by as much as 4 in that last place, which also highlights the need, which we don't have here, but you really should have your chemical shifts labeled on your spectrum to at least 3, preferably 4 ppm to minimize those rounding errors. Again, these are the values. And I've also shown underneath the calculated values for the cis and the trans isomers, the ones we calculated a few slides back. For some reason, this is not showing up on the screen, but I do have a cis isomer here. So this is for the cis isomer. And again, these are the values we calculated earlier. And so you could put the chemical shifts in as well, just as we did before, where we have the cis hydrogen B, 7.34. We have our cis hydrogen A. Trans, we calculated 795. We got trans A. And 6.6, we had trans B. And you can see these peaks line up fairly well with the trans calculated values and not with the cis. So here we have both the trans calculated chemical shifts agreeing with what we see on this spectrum, telling us this is likely trans, but the coupling constants also are in that 14 to 18 range. So this also tells us that this is a trans isomer. So we can use both of those to make that distinction. One more example, this is actually a mixture of cis and trans, and you can see that in that we have 2 smaller doublets here, and then 2 larger doublets. Color code those. But again, we also have the 2 larger doublets. So one of these is cis, one of them is trans. And again, we also have for the aromatic peak and for the methyl peak, we've got taller peaks, and we also have smaller peaks. So the smaller ones would be one isomer and the taller ones the other isomer. How do we distinguish them? Exactly the way we've been doing. Calculate your chemical shifts, see what matches up. For the cis isomer, we expect our peaks at about 7.4, and at 6.25 is the calculated values. And for the trans, we expect our peaks to be around 7.7 and around 6.7. And so you can see the smaller peaks agree better with the cis, the taller peaks with the trans. And so we have both cis and trans. The major isomer in this case is trans. But as before, we would also look at coupling constants. And again, we take the difference between these two peaks. This is again also acquired on a 300 megahertz spectrometer. We get 11.7 hertz. That's in the 8 to 13 range. So this is a cis isomer. And if we do it for the taller peak, to take the difference between those two peaks, multiply by 300, we get 17.1 hertz. And so this is trans. So both the coupling constants and the calculated chemical shifts tell us that the taller peak in this case is trans and the shorter peaks are the cis isomer. Okay. And this is something you'll need to do then for your compound as well. You will only have one isomer for this reaction though. All right, then we'll go to the lab report. We do have that due next week. This will be the full report, same guidelines as before, although this time we do have a discussion which we did not have before. The name, date, section number, academic integrity statement, you need to have all of this. about the abstract, when you're writing that, think in terms of what are your objectives and how are we accomplishing them. For this one of our objectives is to synthesize the alkene. Again, the abstract, we are specific. So you would give the name of it, synthesize ethyl 2E3p-nitrophenylpropenoate. You can use something like chem sketch to give you the name. So if you have problems with that, let's see, yeah, this is the name for the right one. How are we doing this? By a Wittig reaction. And again, we name the compounds, the benzaldehyde and the ylide. And how are we going to make another objective then, since we have to react the aldehyde and the ylide, we did not buy ylide, you were not provided with that, you had to make it. So a second objective is to synthesize the ylide. How did we do that? By deprotonation of our phosphonium salts. Again, we're going to name that. You could name the ylide as well, but it's fine if you don't name the intermediates that we do not isolate. So we made the ylide as an intermediate, but we never isolated it. So you can simply refer to it as the ylide. You don't need to name things we don't isolate. We also have the second objective, or I guess really this would be a third one, and that is to identify the product. Did we actually make what we were intending to make, and what was the stereochemistry? And how are we going to do that? Both of those we do by NMR analysis. And then when you write your abstract, we don't say the objective was we accomplished it by, rather you make the objective known by stating what you did. So an abstract would be something like this. The ethyl 2E3p-nitrophenylpropenoate was synthesized. So we're telling what the objective was. It was synthesized. How? Via a Wittig reaction between nitrobenzaldehyde and the ylide. And I've actually named the ylide in the abstract that I've written. You don't need to do that, but you can. Another objective was the ylide was synthesized. How? By deprotonation of the phosphonium salt with KOH. And then, of course, our objective, how was it identified? And we can simply state the stereochemistry and identity of the alkene were determined using proton NMR spectroscopy. We also state results, so we would also state the product was isolated in 72.3% yield. And you could have that at the end, or as I did here, you can have that in the first sentence. It was synthesized in 72.3% yield. So you're giving that, that result up in that first sentence. And really, that's all there would be to the abstract. Details about how it was synthesized, how we conducted the Wittig reaction, how we isolated our product, all of that goes in the procedure. It doesn't go in the abstract. So the abstract is intended for somebody to quickly look to see what we did and see if this is something that interests them. They might be looking at the paper because they're trying to find out how to conduct a particular reaction. They can see, is this something relevant to what I'm doing? And then quickly move on, if it's not, to another paper without having to read through a lot of material. If it is relevant, then of course they would go down and see our procedure as to how they would conduct theirs. Chemical equation, you do need to show all equations that you do or all reactions that you did. So you will have two chemical equations for this. The first is the reaction of your salt with the KOH to make the ylide. The second one is the reaction of the ylide with the nitrobenzaldehyde to make the alkene. So do show both those reactions. If you do more than one reaction, you need to show both, even if you're not isolating a product or that intermediate. We don't isolate the ylide, but we still did those. You'll see again in the Grignard reaction, you're going to have two reactions you're doing. First, you're going to make the Grignard reagent, and then you're going to react that with an aldehyde to make the final alcohol product. And so anytime you've got multiple steps like that, show each of them. Procedure, this should be fairly standard. Third person passive voice. Since you've done organic 1, you should be familiar with this. One comment with the procedure, you do need to make it succinct. We don't give information that's unnecessary. You assume your reader has a certain level of knowledge. Basically, they're familiar with the techniques up to the level that you're at. So for example, it's sufficient to simply say the mixture was heated at reflux for 10 minutes. You don't need to give more information about that. You don't need to mention that you had a condenser or that you used a heating mantle. We assume a person knows how to heat a reaction. We assume that they know what a reflux is and they can assemble that equipment on their own. Likewise, if you do an extraction or if you wash something, it's sufficient to say it was washed with 15 mils of ether. You do need to state the volume that you used and the solvent, because we could wash with 20 mils and use something else like methylene chloride or ethyl acetate. So you do need to specify those, but you do not need to tell someone it was done in a separatory funnel, that you swirled the layers and that you separated them. All of that is understood when you say washed. You don't need to give any more detail than that. Likewise, as I mentioned earlier, the reflux, you do need to state how long, because we can reflux for any length of time. It could be 10 minutes, 10 hours, 10 days. So reflux, but then simply state how long and no more information is necessary. Solution was washed with 10 mils of diethyl ether, and it's understood the layers were separated. Likewise, if you're doing a recrystallization, you can simply say it was recrystallized. You do need to state what solvent you used, and typically we give the approximate volume. Nobody actually measures the exact volume for a crystallization, but we usually know about how much we used, and that's it. It's expected the person knows how to do that they have to heat the solution, they dissolve it in the hot solvent, and then they cool it to get the material to recrystallize out. So procedures should not have excess information. Anytime you report quantities, also report moles or millimoles, and you can have that in parentheses right afterwards. So you can simply have 2.78 grams, parentheses, the number of moles or millimoles. And if it's a solution, you could have something like 6.7 milliliters and then 6.7 millimoles, but also give the concentration. So for this, it would be a 1 molar solution. And then state what it is: sodium hydroxide, KOH, ethyl bromoacetate, whatever it is. But you can specify it in that way, and it's understood the millimoles and the molarity go with that compound. Report yield and percent yield. And again, you can simply state the mass yield and then in parentheses immediately afterwards the percentage. If we do melting point or boiling point, you would mention that, but also give the literature value. And then spectral data at the end of the procedure. The formats are given here. We'll see these again. You should be familiar with the IR already from Organic 1. Likewise, the NMR Organic 1, also the NMR assignment that you had. You were expected to do this. If we do the other ones, I'm pretty sure we're doing mass spec. I don't know if we're still doing UV. I think that's been removed. But the formats are fairly similar in that you state the technique. So for NMR, we give that. We state what medium we're using. For IR, it's usually done on a salt plate. And so we would say KBR. NMR, we're doing a solvent. We use deuterochloroform, so we would specify that. We give the units. For IR, it was inverse centimeters. For NMR, it's ppm. And we list our frequencies, but for NMR, we don't list actual frequencies. Actual frequencies would be hertz, but that's somewhat meaningless. We use a normalized one that eliminates the effects of the field, and also one that's referenced to some standard like to EMS, tetramethylsilane, as a 0. And we designate then that we're looking at a proxy for frequency, and that is our chemical shift. And so we put a delta there. That delta represents chemical shift. And then after that, we give the chemical shift, the splitting, the integration, semicolon, chemical shift, splitting, integration. And you would do that for each of the peaks that's present in your spectrum. And the common abbreviations are given: S for singlet, D for doublet, T for triplet, Q for quartet. M for multiplet, and anything else you would spell out. So quintet, we would spell out rather than putting a Q that's already taken. Likewise, sextet, septet, we already have the S reserved for singlet, so those you would spell them out. For calculations, limiting reactant, theoretical yield, percent yield, and the calculations do need to be based on the amounts you actually measured. The procedure may say to use 5 millimoles or 10 millimoles. Don't start with that because you probably do not have exactly 10 millimoles, and you certainly did not measure millimoles. Start with what you measured, which is either going to be a mass or a volume, and then calculate moles of the starting material from that, and then mole to mole ratio, and then you can calculate theoretical yield for your product. For limiting reactant, I recommend calculating theoretical yield for each reactant, and then whichever one is least is your limiting reactant, of course. But if you do it that way, you don't need to show a second calculation for theoretical yield. So if you do your limiting reactant calculation for your phosphonium salt, for the KOH, and for the aldehyde, if each of those calculations is a theoretical yield calculation, you've already done theoretical yield. You don't need to show it a second time. That's part of your limiting reactant calculation. For this experiment, you do have 2 more calculations you need to show. You do need to show the calculation for chemical shift for the cis and trans hydrogens, and also the coupling constant for the 2 vinylic peaks in your spectrum. It is important to use proper significant figures. We have an example here where the calculations are done and the amounts of product is done to only 1 significant figure rather than fully carrying it out. If we do this using proper significant figures, you can see we get different numbers. First, here it looks like it doesn't matter which one, they're equal. We don't have one as limiting, when in reality, we actually do have one that is the limiting reactant. And it also shows that we have differences then in the theoretical yield that we calculate. So do use proper number of significant figures. I'm going to pause here for just a minute, talk about one thing that may be coming up with the chemical equation. The lab protocol for this shows the reactions that we're doing, and compounds are numbered. And so for the product, you'll have something like this, where it's showing the product, the nitrophenyl, and showing the ester, and specifically in this case, the trans, and underneath is a 5 that's in bold font. Do not refer to this compound as trans 5 or the complementary one as cis 5. The numbers, and it's okay to number compounds like this, but you need to always start at 1. In the lab protocol, Dr. Donahue, when he wrote that, did start with 1 compound as compound 1, and then went on from there. If you only have this as, say you've got your, and I'm going to make this real abbreviated, we have the salt going to ylide, and then ylide to alkene. If you want to number them, you're welcome to do that, but in your case, you would have salt as 1, ylide as 2. And since this is the same ylide, this is still compound 2, your alkene would be compound 3. So you can refer to it that way, and then you could call yours 3 cis or 3 trans, but you do have to show what the numbering is so we can see that. This 5 is an abbreviation. And this is something, if you look in the chemical literature, you will actually see this commonly used. You will have equations, and underneath the compounds, you'll have numbers. And then in the text, you'll have a number. It might say something like a solution was made by dissolving numbers. Let me try again. 6.72 grams and then you can have 5 afterwards. But you will have had to define it. An alternative would be to say this is nitrophenylpropene 08 and use the abbreviation NPP. And then in the text, instead of having a 5 here, you could simply have NPP as the abbreviation. The number substitutes as an abbreviation, but as with abbreviations, you have to show what they are. The first time you would name your compound, you could put NPP in parentheses afterwards, telling everyone, this is the abbreviation I'm using for this compound. Or you can use the number and say, this is the abbreviation I'm using for the compound. But you do have to tell your reader what that references. All right, so let's move on then to discussion and conclusion. In the discussion conclusion section, you present your data and tell us what the data means. Did you make what you were intending to make? Did you make something else? How do you know? All spectra need to be presented in tables. So for NMR, which is the only spectral data you have for this one, you would have a table with 5 columns, chemical shift, the type of hydrogen, the splitting, the integration, and then also an assignment. So you're going to assign each peak to a particular hydrogen in your compound, which means you also have to have a structure drawing, and this should be next to your table, that has all of the unique nuclei labeled. So in this case, you can see the methoxy, we labeled A. The equivalent hydrogens are given the same label. So these are both labeled hydrogen B because they are equivalent to each other. These are given the same label C because they are equivalent to each other as well. And then again, the 2 methyls for the isopropyl group are equivalent, so we give them the same label. But you do need to have a labeled structure, otherwise we don't know what the labels mean in your table. So your table would look something like this. We have a peak at 6.84, hydrogen type, aromatic. Splitting was the doublet of doublets. Of course, you could also call it a multiplet. Integration was 2 hydrogens. Assignment, hydrogen B. And so you would do that for each of the hydrogens. If you have 5 hydrogens, 5 unique hydrogens in your structure, you should have 5 rows. If you've got 6 unique hydrogens, you would have 6 rows. So this table is actually short a couple since I only have 3 of the hydrogen shown, and also I've left out 2 of the peaks. So you could go back. This is from the spectrum we analyzed at the very beginning. Then, of course, you're going to have a discussion of the data, and the discussion should be able to stand independent of your table. Meaning, if I delete the table, I should still be able to understand your text. If I can't read your discussion, the text, and understand it without having to go back to the table, your discussion is deficient. So start off by telling me what is there, and then telling me what it means. So for example, there's a peak at 2.7 ppm. That peak is a septet and integrates to 1 hydrogen. So now I know what's there. And so then you can tell me what it means. 2.7 ppm is in the benzylic region. The splitting indicates it has 6 neighbors, suggesting 2 neighboring methyl groups. And then you can say this correlates with hydrogen, what was D in that structure on the previous slide. This is hydrogen D, or this points to an isopropyl group. But give that structure. Do make the assignments though. This peak correlates with hydrogen A or hydrogen B. But do that for each one. You'll have little paragraphs like this. This one had 5 peaks, so you'll have 5 little paragraphs like this. And that will then probably 1 summary paragraph then telling you this is the compound, whatever it is that you're looking at. If I see a discussion like this, hydrogen E is a saturated methyl group with 3 hydrogens. It has 1 neighboring hydrogen, hydrogen D. So There are 2 of them, so it's going to have an integration of 6. If I see that, you'll see this. Think about it. What is wrong with this discussion? What is this discussion doing, and what are you supposed to be doing? If you think about it, you're supposed to be interpreting an NMR spectrum. This discussion never mentions the spectrum. It starts with the conclusion that the compound is this one here. This would be methyl anisole, or excuse me, isopropyl anisole, but doesn't matter too much what that is. But anyway, it's starting with the conclusion and then trying to draw data from the conclusion. It is saying, if I actually have this, this is the spectrum or the data I expect. But that's backwards. Don't start with your conclusion and tell me what you expect for data. Start with your data and tell me what you expect. You should always start with the spectrum. Tell me what's there. Is there a peak? What's the splitting? What's the chemical shift? And what's the integration? And then tell me what that means. Go from the spectrum, draw a conclusion. How does this correlate to the structure? Never start with your structure, because then you're going from data, from conclusion, and you're drawing data, and we simply don't go that way. That's backwards. All right, then we will go to the spectrum. I've got a couple here in this presentation I'm going to look at, but I think maybe I'll abandon this and go to the actual spectra. But your spectrum should look a bit like this. Actually, let me back up one. There are 2 peaks here that are important to recognize. This one here, and the size of this peak is going to vary depending on how concentrated your solution is. But this is chloroform. In NMR, you're always going to see a little bit of your solvent. It is possible to buy solvent that is 100% deuterated, but typically it has a small amount of proteosolvent. So we used deuterochloroform, so we have CdCl3, but it is contaminated with tiny amounts of proteochloroform, and so we'll often see a chloroform peak. So when you see a peak at 7.28 ppm, that is chloroform. You can ignore that peak. You typically don't want to integrate it, don't need to do peak picking, but recognize that's there. And again, if you have very dilute solutions, it can be a large peak. If you have more concentrated solutions, it's often small enough that you won't notice it. But this is going to be present in some spectra. Recognize it, ignore it. If you use deuteroacetone, you'd have a peak at a different place. In fact, for acetone, it's around 2 ppm. But we do have one other singlet that's important, and this is going to be around 1.6 ppm. And this is water, or actually it's going to be more likely HOD, water where one of the hydrogens might have a deuterium on it. But for chloroform, the water typically shows up right around 1.6 ppm. So if we took a spectrum of chloroform without anything dissolved in it, just took it right out of the bottle, we would have those 2 peaks. And again, you can ignore that. Typically, it will be a fairly small peak, but again, if you have a very dilute solution, if you only put a small amount of material in your NMR tube, you may see that. You can ignore it. This is the same spectrum. I've just expanded up on that region between about 6.5 to 8.5 ppm. I want to highlight this peak here. For some of your spectra, the 2 peaks that are real close together, these 2 right here, notice there are 2 peaks. For some of you, you may find this, it looks like just 1 peak there. And there's a total of 3 rather than 4. That's fine, but whichever one you have, a few things, if you see it even as 3, this is not a triplet for the simple reason it's not a 1-2-1 pattern. Also, the 3 peaks are not equally spaced. Or in this case, 4, But again, it's not a quartet because it is not a 1-3-3-1 pattern, and those 4 peaks are not equally spaced from one another. What we have here is 2 doublets that are overlapping to a bit. So we have one doublet here, and we have a second doublet there. And you can calculate coupling constants for each one and figure out what those are. And something I mentioned earlier, if 2 peaks are splitting each other, the coupling constant will be the same. And you can just kind of eyeball it here. The distance between the 2 peaks that I've marked with the red is about the same as those 2 peaks. So those peaks are splitting each other. And then the other doublet, which I'm going to be marking here in green. So this doublet, the spacing between those 2 peaks is about the same as the spacing between these 2. So these 2 peaks are splitting each other, and these 2 peaks are splitting each other. Okay, so that will help a little bit with assignments when you're making those, if you think about that in terms of the splitting. And then if you look at the integration, I don't know how well it's showing up on the screen, but the integration here is roughly 2. It's 1.99. This one is 3.08, so 3 hydrogens. This one, again, we're ignoring because that's the chloroform, our residual solvent. And this other peak here is 1 hydrogen. In fact, that one's set to exactly 1.00. Those 2 doublets, the only way you can get 3 is if one of them is 2 hydrogens and the other one is 1 hydrogen. And obviously, the bigger one has to be the 2 hydrogens because peak size is directly proportional to the number of hydrogens. And then the smaller one would then have to be just 1 hydrogen. So when you see that in your spectrum, you can recognize it's 2 peaks there that are overlapping. And that also accounts for the fact that we have 3 hydrogens. This is another spectrum that, in fact, most of your spectra look like this. The thing to note that's different from this one from the others is we actually have 2 quartets. We have a smaller quartet and a larger quartet. We have a smaller triplet and we have a taller triplet. If you look at the integral ratios, these are really nice. This 2 to 3 to 2 to 2 to 3. And then we get a little bit of an oddball with the tall ones in that the relative integration for the tall ones is 6.37 and 9.7. And so those integrations don't match very well. They're not close to whole numbers compared to the other ones. But if you think about it, we have a nice 2-3 ratio for the smaller quartet triplet. For this one, this is 2 hydrogens to 3 hydrogens if we compare the 2 taller quartet triplet. Think in terms of chemical shift. Around that 3.5 to 4.5 or 3 to 4.5 range is our OCH. This is 2, and this is 3 hydrogens, CH3. Quartet tells us this is bonded to a CH3. Triplet tells us it's bonded to a CH2, so those 2 are bonded to each other. And of course, we have the same thing with the ones that are in green. We have a CH2. Again, it's in that alkoxy range. And then the smaller triplet is a CH3 relative to each other. And the splitting, the quartet tells us bonded to a CH3. So we have these 2 ethyl groups or 2 ethoxy groups. One matches with the peaks that we would expect in the rest of the compound. So the shorter ones would be part of the compound. The other 2 are something else. And if you think about what you used in the reaction for your solvent, for your washes and stuff, the other peaks are probably from the solvent from your reaction. And so you may see that. In fact, for pretty much every spectrum, I think for this class, you guys just didn't leave it in the oven long enough, or the oven wasn't hot enough, or a combination of those two. You're going to have this issue. Let me minimize the PowerPoint presentation, and I'm going to bring up actually a couple of things I'm going to bring up first. As you learn, if you go to my folder, you'll find your spectra are uploaded. If it's not fully expanded like this, if you see this with where you don't see your spectra, you see just the folder, click on that little arrow and it will expand it and you can see your particular spectra. I suggest downloading yours and processing it just to look at it and see what it actually looks like. But for this report, you might decide that you'd rather use this one. I have also uploaded a clean nitropropene 08 spectrum. If you download that one, this one doesn't have any solvent in it. And in that case, you'll see a spectrum. Well, this is not the clean one. This is another example of the two quartets. In this case, the solvent is smaller than the sample, and our integrations aren't normalized. In fact, this one hasn't been properly processed. You can see this was done automatically, and the computer integrated this OH peak and both triplets together. You will need to process your spectra when you download that. Delete the old spectra and integrate the new ones. Let me jump real quick over to, yes, this is one that's clean. The clean spectrum looks a lot like this. Again, it's not properly processed, so you would go to Analyze and Integrate. I am using Topspin, but I'm using version 4, so it looks a little bit different than what you have if you have version 3. For this, you have an icon. Again, mine looks a little different, but if you hover on it, it says deselect all regions. You can select all of them. And then next over is delete the selected regions. Click on that, and it will get rid of all of the old integrations. And at that point, you can integrate. This icon does need to be highlighted to define the regions. If it's not, what you're going to get then is an expansion, which is fine. It might actually help with the integrations to start with, but then click and you can integrate each one. And as I mentioned, the first one in this program is going to be integrated to 1 hydrogen, and then the others two are based on that. And we do have our chloroform at 7.28, roughly 7.27 here. And you'll see we have an integral here of half a hydrogen. Don't like that, so we're going to tell it to calibrate the current integral and tell it to set it to 1. And when we do that, then of course the other ones are adjusted as well. Now this is 3 and this is 2. But something to note, I mentioned earlier that this is that 2 doublets. In this case, the inner peaks are overlapping enough that you don't even see them as separate. But we do have that integration there, or that overlap there. Let me undo my earlier zoom, unhighlight. Actually, we can just leave that highlighted, integrate from here. And we should have our nice near whole number values for these. And we can ignore the other peaks. Typically, you'll see a peak right around 0 as that's TMS. It's not always there. A lot of times, in fact, I prefer to buy solvents that don't have TMS, but it looks like the stockroom did buy chloroform that has a little bit of TMS as a 0. Most people these days don't use TMS as a 0. They'll in fact use the chloroform peak as the reference and set it to exactly 7.27 or 7.28 as the reference and fix it that way. So this is what the spectrum should look like. We can tell it return and save. And again, you'd also do your own peak picking. You'll notice we have peaks set here. For these little ones, we don't really want those. So we can tell it to do the peak and do that. And if we highlight all of our peaks, it will actually erase the ones that we're not picking. And so we can do that. Remember, with this program, you do need to have the tops of the peaks in here. So if I do this, notice the tops of that quartet are not inside the box. We will lose those shifts and we only have the two outer ones. You do need to have all of them in if you want to have those in. And again, you want at least 4 peaks for the vinylic one so that you can calculate the coupling constant with some accuracy. One other thing, let me come back to the As You Learn site. Scroll down a little bit. You will also see we have the Wittig PowerPoint. So the PowerPoint that I just went over is here. Have a good evening.